spans R2. So this is similar but a little different, okay? What we're talking about is spanning R2, and what that means is just proving that these two vectors can represent any individual vector in two dimensions, okay? So we have to prove this. And by proving this, we know what we've talked about before. We know we're probably going to have a scalar of each of these, okay? So we're going to say scalar A of, we're going to call this maybe vector, I don't want to say xy, m and n, okay? Vector m and vector n, we're going to call it, okay? So some scalar of vector m, which is, those are the components, along with a scalar of vector n is going to be equal to, now we don't have a specific value because we don't have a specific vector to represent. It's asking us to represent every possible vector in two-dimensional space. So we're going to use a variable because these can be any numbers, and we're going to use the variables x and y because those are the axes we use. So we know that we can represent any single number for the x, and we can represent any single number for y. In other words, we can represent any vector in two space with these two as long as we have scalars of them. So we're going to prove it, and we're going to show equations that would span the two of them. So the same idea, what we're going to do is distributive property 2a and a plus negative 3b and b is equal to x and y. So we have an extra variable. Now what we're going to do is we're going to turn these into equations. So we know that 2a minus 3b will give us x. So 2a minus 3b is the equivalent of x. Okay. And we know that a plus b is y. Oh, that's nice. Did I do that right? Oh, you know what? This is supposed to be a negative one. It doesn't really matter because technically any vectors will span it. But let's just go along with the textbook. That way you guys can compare when you finally get one. Equals y. A minus b is equal to y. Okay. So I have two equations here. But what I want to do is I want to set both of these or represent both of these of values of a or b. Essentially, I want to find out what a could equal and what b could equal. Okay? And the reason I'm doing that is so that I can find points in two-dimensional space. In other words, so I can find values of x and y. So I'm going to take the very first one, which is our first one. Actually, what we'll do is we'll do some elimination here to solve this. Actually, let's substitute. I much prefer it. Okay. First equation, we'll solve for a. So 2a is equal to x plus 3b. In other words, a is equal to a half x plus 3 over 2b. Okay? So we can substitute to solve that. Oh, you know what would be much easier if we'd done this one. Let's start with the bottom one. That way we're not working with fractions. Let's say a is equal to y plus b. I just realized that. Much easier to work with. We're not working with any fractions. Sometimes you'll come across that. It might have been easier to go with the other one first. So let's work with equation 2 and plug it back into equation 1 for a. So equation 1, we have 2. And instead of a, we're going to replace a with the value of y plus b. Minus 3b is equal to x. So this will help us solve for our variable b. Okay? So we're going to have 2y plus 2b minus 3b is equal to x. When I combine these, I'll get negative b is equal to x minus 2y. And in other words, b is equal to 2y minus x. Okay. So I've now solved for a scalar of b. And what that means is I can plug in any x value I want. So any component or any point on a graph as an x and a y value, and I can find out for what scalar of our original vectors, which were these two, what scalar of this vector will eventually make this. Now I still have to find out for the scalar of a also. So let's go down. We know that b is equal to that. Let's go back into equation 2 because it's so simple to use. We're plugging for b. So minus 2y minus x is equal to y. This is equation 2 again. All I did was sub this value in for the b. Okay? So when I do that, we get a minus 2y plus x is equal to y. A is equal to, when I bring the 2y over, it's going to become positive, so it'll be adding, so we'll get 3y minus x. Okay? So what I've done is I found the scalars, or I found equations for each of the scalars. And what I mean by that is I can now find a point. So let's just look at the entire page here. These are what's important. I found an equation for b and an equation for a. So with these two vectors, I can find some number for a and some number for b. And using these two vectors, I can find any combination. Okay? In fact, let's just make up one, just to prove this. What component point would you guys like? Let's give me a number. Give me some coordinates. 5, 6. Okay, let's see if we can find 5, 6. So, we're going to look, we're trying to find the vector that is at point 5, 6. Okay, starts at the origin, goes here. We knew our set, if you guys remember our set, we started with the numbers 2 and 1 and -3 and -1, correct? Now as long as we've done this correctly, we should be able to get this, no problem. We're going to put a scalar in front of it, and these are our scalars, these are the values of them. But instead, what we're going to do is we're going to plug in, this is the x value and this is the y value, so we're going to plug those in for the x's and for the y's in here to find out what scalars of these two vectors would give us vector at 5, 6. So when we go to plug it in, we'll plug in a first, since a is technically for this vector here. We get 3, y is the number 6, and the number 5. A is equal to 18 minus 5. A is equal to 13. Okay? So the very first part of this set, we know that 13, 2, 1, and then let's figure out what the other one is. The equation for b, whoops, is 2y minus x. So 2, y is the number 6, minus x again is 5. We get 12 minus 5 is equal to b. b is equal to 7. So plus 7, -3, -1 will give us this component vector of 5, 6. So no matter what the number was, once we found that equation, we were able to find scalars of it.